Physics Part 44. Between A and B, the particle is slowing down because the distances traveled in equal periods of time are getting smaller. The average velocity during the period is x2 minus x1 divided by t2 minus t1 on the graph. This is represented by the gradient of the straight line joining A and B. At B for a moment, the particle is at rest. And after B, it has reversed its direction and is heading back towards the origin. Between B and C, the average velocity is x3 minus x2 divided by t3 minus t2. Because x3 is less than x2, this is a negative quantity, indicating the reversal of direction. Calculating the average velocity of the particle over the relatively long intervals t1, t2 minus t1 and t3 minus t2 will not give us the complete description of the motion. To describe the motion exactly, we need to know the particle's velocity at every instant. We introduce the idea of instantaneous velocity. To define the instantaneous velocity, we make the intervals of time over which we measure the average velocity shorter and shorter. This has the effect of approximating the curve displacement time graph by a series of short straight line segments. The approximation becomes better the shorter the time interval, as illustrated in our figure. Eventually, in case of the extremely small time intervals, mathematically we would say indefinitely small. The straight line segment has the same direction as the tangent to the curve. This limit case gives the instantaneous velocity the slope of the tangent to the displacement time curve. Displacement time and velocity time graphs. A sketch graph shows how the displacement of a car traveling along a straight test track varies with the time. We interpret this graph in a descriptive way by noting that between O and A, the distances traveled in equal intervals of time are progressively increasing. That is, the velocity is increasing as the car is accelerating. Between A and B, the distances for equal time intervals are decreasing. The car is slowing down. Finally, there is no change in position. Even though time passes, so the car must be at rest. And as we move along, we find very interesting facts over here. And there is no change in the position. Between A and B, the distances for equal time intervals are decreasing. The car is slowing down. Finally, there is no change in position, even though time passes. So the car must be at rest. We can use figure to decide the details of the way. And we can deduce some facts on what kind of a way it covers. And this is how the velocity is varied with the time. To do this, we draw tangents to the curve in our figure at irregular intervals of time.